All right, so now we're going to look at so-called type 2 improper integrals. These you have to really keep an eye out for because they will not have an infinity symbol in them anywhere. What makes this one improper is that 1 over the square root of x is undefined at x equals 0. And in fact, the graph of y equals 1 over the square root of x has a vertical asymptote at x equals 0. So here's how we're going to set this one up. And I am going to switch over to my tablet and talk you through how this works. All right, here we go. So since this function has a vertical asymptote at x equals 0, the way that we have to set up this integral is to imagine a number a. We're going to take the integral from a to 1, and then we're going to let a approach 0 from the right. So that's going to look like this, integral a to 1, limit as a approaches 0 from the right. All right, and I'm already thinking ahead to the antiderivative for this 1 over the square root of x. So I'm going to write that as x to the negative 1/2 by the backwards power rule. That antiderivative is x to the 1/2 divided by 1/2, so 2x to the 1/2. Plug in 1, plug in a. And what you get out of that is 2 minus 2a to the 1/2, which is 2 minus 2 square root of a. As a approaches 0 from the right, that second term goes to 0, and this limit is equal to 2. So now if we switch back to the slide, that picture makes a little more sense. So when the integral is from a to 1, that area is 2 minus 2 square root of a. And then let a approach 0 from the right, the area is equal to 2. All right, so again, this will make a lot more sense when we do some examples. Again, these are called type 2 improper integrals. So the first type is where f of x is continuous from a to b except at the number a. So that's like the one we were just looking at. So in that case, you take the integral from c to b and let c approach a from the right. The second type is where the function is continuous from a to b except at the number b. So what you would do then is instead of integrating from a to b, you would integrate from a to c and let c approach b from the left. Total alphabet soup here. I know it's terrible. The first time we do an example like that second kind, I'll draw a little picture. When you draw the picture, it really makes a lot of sense. And the last type is where f of x is discontinuous at an interior point of the interval. And what you have to do then is take that integral from a to b, break it into the integral from a to c, plus the integral from c to b. And then the integral from a to c is going to be like the second type here. The integral from c to b is going to be like the first type. And the terminology converges and diverges is the same as it was under type 1. If that limit is finite, we say the improper integral converges and that the limit is the value of the improper integral. If the limit does not exist, the integral diverges. All right, so here are the examples we're going to be looking at under type 2 improper integrals. So I will switch over to the tablet. All right, so the first thing I want to be sure to mention about this is that this is not part of that discussion from earlier about the integral of 1 over x to the p from 1 to infinity. And the reason it's not part of that is because this integral is not from 1 to infinity. It's from 0 to 1. So that rule that we derived there, which I believe was called theorem 3, or it was definitely example 3. I don't know if they made a theorem out of it. That does not apply to this example. All right, so we definitely have to do this one from scratch. It's very similar to the one we just did. 1 over x to the 0.999 has a vertical asymptote at x equals 0. So we're going to make this integral from a to 1. And I'll go ahead and call this x to the negative 0.999. And then eventually we will let a approach 0 from the right. All right, and once again, by the backwards power rule, that antiderivative is x to the power negative 0.999 plus 1, which is x to the 0.001 divided by 0.001. Plug in 1, plug in a. All right, so that is going to give us, and instead of dividing by 0.001, why don't we call that times 1,000? Plug in 1, you just get 1. Plug in a, you get a to the 0.001. Now remember, a is approaching 0 from the right. So again, you can think of this as the 1,000th root of a. As a gets closer and closer to 0, so does the 1,000th root of a. So this term is going to disappear, and this limit is equal to 1,000. So another fun, mind-blowing fact, let's just call this example 1.5. If you tweak that exponent just a little bit from 0.999 to 1, you get integral from 0 to 1 dx over x. And again, you have to write that as limit a approaches 0 from the right, integral a to 1. Okay, and we know that integration rule, that's natural log of x. It's actually natural log absolute value of x, but we're on an interval of positive numbers here, so I don't have to write that. All right, so that's going to be the limit as a approaches 0 from the right. Natural log 1 minus natural log a. Natural log of 1 is 0. And if you picture the graph of y equals natural log of x, as x approaches 0 from the right, natural log of x approaches negative infinity. So just by tweaking that exponent from 0.999 to 1, this integral diverges. So that's, again, kind of a mind-blowing fact, I think. Okay, here's the next example, the integral from 0 to 1 of 4r over the square root of 1 minus r to the 4th dr. I'm trying to resist the urge to make an RDRR joke, but I guess I just failed. All right, notice that this is an improper integral because this expression is undefined when r equals 1. So what I'd like to do with this one actually is to deal with the antiderivative first, because this is an interesting enough problem without it being an improper integral. So let's do this part. We'll get our antiderivative, and then we will deal with the improper integral part at the end. Okay. You may have seen an integral like this in chapter 7. The secret is to rewrite it like this: 4r over the square root of 1 minus the square of r squared. All right, we're trying to make this look like one of those inverse trigonometric integrals. So I'm going to let u equal r squared, which is going to make du 2r dr. And why don't we build the 4 in there? I'll multiply both sides by 2. And then 4r dr will get replaced with 2 du. All right, so then we'll have 2 times the integral du over the square root of 1 minus u squared. So hopefully you recognize that one from chapter 7. The integral of 1 over the square root of 1 minus u squared with respect to u is inverse sine u. But of course, this isn't about u. This is about r. So the antiderivative we're looking for is 2 inverse sine of r squared plus c. Okay, so back to our original integral. It was from 0 to 1, 4r dr over the square root of 1 minus r to the 4th. So because this expression is undefined when r equals 1, in fact, it has a vertical asymptote there, we're going to write this as the limit as b approaches 1 from the left. So let me just stop for a second and explain why it's set up like that. Suppose the graph of this function, I don't really have any idea what it looks like, but suppose it looks something like this. We're trying to find the total area under that curve. So what we're going to do first is put a number b right about here, and then we're going to let that number b creep closer and closer to 1 from the left. Okay, so integral from 0 to b, 4r dr over the square root of 1 minus r to the 4th. All right, we have that antiderivative. We got that out of the way at the beginning, so that's going to be 2 inverse sine of r squared. Plug in b, plug in 0. Which gives us the limit as b approaches 1 from the left of 2 inverse sine of b squared minus 2 inverse sine of 0. All right, as b approaches 1 from the left, b squared also approaches 1 from the left. So the limit of this piece right here is going to be the inverse sine of 1, which is pi over 2, right? So this thing comes out to 2 times pi over 2. And the inverse sine of 0 is 0, which makes the value of this integral equal to pi. So what we say is that this improper integral converges and its value is pi. Integral from 0 to 2 of 1 over the square root of the absolute value of x minus 1. Excuse me while I break up a dog fight. Okay, so there's one thing I want to get out of the way about this, and I'm not sure we have ever in this class encountered an integral with an absolute value in it before. Remember back to Calc 1, and hopefully even before Calc 1, the piecewise function definition of absolute value. The absolute value of x minus 1 is equal to just x minus 1 if x minus 1 is greater than or equal to 0. However, if x minus 1 is negative, then you have to flip it to the opposite. So it's going to become the opposite of x minus 1 if x minus 1 is negative. And that is going to be an issue in this problem. the vertical asymptote of this function occurs at x equals 1, which is an interior point of the interval from 0 to 2. So the first thing I have to do is break this into two integrals. First one goes from 0 to 1. And then from 1 to 2. All right, and now since that's broken, according to this piece, well, not according to, but it lines up with that piecewise definition. So let's start with the second integral. On the second integral from 1 to 2, x minus 1 is non-negative. So we can write this integral as just dx over the square root of x minus 1. We don't need the absolute value. However, on the other integral, 0 to 1, x minus 1 is negative on that interval. So what we have to do with that is write it as the opposite of x minus 1, which I am going to write as 1 minus x. Okay. All right, so there's a little bit of extra housekeeping in this problem. Now I'm ready to write these as limits. So remember, the asymptote occurs at x equals 1. So the first integral will become limit as a approaches 1 from the left, integral 0 to a. And you know what? Just to save a little bit of time, let's write this as 1 minus x to the power negative 1/2. It's going to be more backwards power roll. And then the second limit will be the limit as b approaches 1 from the right, integral b to 2. And again, let's write this as x minus 1 to the negative 1/2. Okay. All right, so now I'm ready to start looking at antiderivatives. Okay, this one here, the first one, this is going to be a backwards power rule and also a little baby u substitution. So the antiderivative for this is 1 minus x to the power 1/2 divided by 1/2, but also divided by negative 1, because the derivative of 1 minus x is negative 1. Okay. So limit as a approaches 1 from the left, and then we're going to plug in a, plug in 0. For the other one, it's the same thing, except we don't have the baby u substitution issue because the derivative of x minus 1 is just 1. So this one is just going to be 2 x minus 1 to the 1/2. Plug in 2, plug in b. Okay. All right, so now I'm ready to plug in those limits. So we're going to go limit as, I was saving that for, okay, let's do this. All right, I have to use the top of my screen. I should have left 2 pages for this one. I don't know why I didn't. All right, let's just go up here. Probably make it easier to follow anyway if I stay on the same page. Okay. Limit as a approaches 1 from the left. We have negative 2, 1 minus a to the 1/2 minus negative 2 times 1 to the 1/2 plus the limit as b approaches 1 from the right of 2 times 1 to the 1/2 minus 2 times b minus 1 to the 1/2. All right, so as a approaches 1 from the left, this term is just going to go to 0. And as b approaches 1 from the right, this term is going to go to 0, leaving us with a 2 and another 2. Who would have ever believed calculus 2 is just 2 plus 2, but in this case it is. And the value of this integral is 4.